Good evening, everyone. This is week two of live session for the course Computational Fluid Dynamics by Professor Srinivas Jayanti. So we'll start this session for today. Just a minute, I'll just share again. Good evening, everyone. This is live session two for course Computational Fluid Dynamics by Professor Srinivas Jayanti. I am TA Ankara Kartiga. I am from the Department of Chemical Engineering from IIT Hyderabad. So we'll move on to question 1. In here it is a case whereby this case will be followed by few questions. So based on this we'll answer the questions. So here it is given that you wish to solve a problem involving steady state heat conduction with a source term. In case of one dimensional flow, this takes the form k d square t by dx square is equal to q, where k is the thermal conductivity of the material, T is the temperature, Q is the volumetric heat generation rate. For this case, answer the following questions. So, in this case, it is given that we are solving a problem involving a steady state heat conduction. For it is a one-dimensional flow and it is given by this equation Q is equal to K d square T by dx square, and it is given K is thermal conductivity, T is temperature and Q is volumetric heat generation rate. So based on this case, we'll answer the following questions. The first question is, For equation 1 to be dimensionally consistent, the units of Q should be what? So they have given a few options. So we will see how to solve this first. So it is given that Q is equal to K T square T by dx square. If there is any issue, please say it. Okay, you are saying options. So K, we know the unit of K to be watt per meter Kelvin. And T is Kelvin. And bottom we have meter square. So this Kelvin and this Kelvin gets cancelled. So it will be watt per meter cube. And that is equal to joule per meter cube second. Answer is option 4. Someone else also told answer is option 4. So the next question is, we wish to solve for steady state temperature distribution in a rod of length L and the variation is only axial. Which of the following boundary condition combination is admissible? So here it is given that we are solving the temperature distribution in a rod whose length is L and the variation it is given, it is a one-dimensional problem. So what are all the boundary condition combination that can be used for solving this problem? The first is temperature at both the ends is given. So here temperature and the temperature over here is given. Let's keep it TA and TB. And the heat flux at both ends is given. So heat flux here and heat flux here it is given. This is option 2. Or else heat flux and temperature at one end. In one of the end heat flux and temperature is given, or in the last option heat flux at one end and temperature at one end is given. So basically to solve any computational fluid dynamics problem, we need boundary conditions where the values of the boundaries are given. So on seeing with the help of the boundary conditions only, we will be able to solve the problem in a step-by-step process. So to solve this problem, we absolutely need, there are few of these boundary conditions can be applicable. The first one where temperature at both the ends is given. From this we can able to solve the problem. Like if temperature at this end and this end is given, we can use this to move in the progression. So we can solve temperature at all the points. Heat flux at both the ends is given. If heat fluxes at both the ends is given, if we cannot solve the problem because both will be a derivative, and so like we may not be able to get the proper values at all the points. So this condition is not applicable. So whereas this is we can do it. And heat flux and temperature at one end is given. If both the values are given at one end, we do not know how the temperature is moving in this direction. So this option does not give is not applicable to solve the system properly. The next option is heat flux at one end and temperature at the other end. So in this option, heat flux is given at one end and temperature at other end is given. So basically this option is also feasible as we know the temperature at one end. So by solving this we can obtain that uh, option 1 and option 4 is right. That is it is option 3 is the right answer. So for the question 2 the answer is option 3. That is 1 and 4 is 1 and 4 can be used in two different situations to solve this case. For equation 1 to be one dimensional, q can be of the form q is given as k d square t by dx square. So here it is variable of x, and also it is q can be constant. So option 1 and option 2 can be applicable in this case. So the answer for this problem is 1, where q is equal to k d square t by dx square. So it can be a function of x, that is position, and also it can be a constant. So next is the problem. Here it is given that which of the following is an admissible extension of equation 1 to steady heat conduction in two dimensions? So it was given that q is equal to k d square t by dx square. That is the one dimensional problem. If it is extended to two dimensions, which of the following equation or which equation can be used to solve that? So in the first equation, it is given that k dou square t by dou x square plus dou square t by dou y square is equal to q x and y. Here the k is given only for dou square t by dou x square. I mean it is not given in this term, so this is not applicable. And the next option, it is given that dou square t by dou x square plus dou square t by dou y square is equal to 1000. Here q is given as constant, and also it is left hand side is a can be it's similar to the first equation where q is equal to k d square t by dx square, where it was given that k is a constant. And so option 2 is admissible. We'll see option 3. It is given that dou t by dou t is equal to alpha dou square t by dou x square. It is given steady state heat conduction. This term won't be will become 0 in this case. So this is not an appropriate extension of equation 1. So the answer is option 2. That is option 2 is the answer. We'll see what is the answer. Option 2 is the answer. Next is the question. You wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold because the cold airflow is not uniformly distributed across the heat exchanger. From this on, these are different problems not related to the case given over there, the first problem. Here it is given that we want to improve the performance of an air-to-air heat exchanger, and by making a suitable design modification or better design, cold airflow is not uniformly distributed across the heat exchanger. So we need to modify this to get a better or improved performance in the heat exchanger. You wish to study this using CFD and arrive at a better design. For this problem, which of the following statements is true? You expect CFD to give you a reasonably correct solution. You expect CFD would not be of much use. You would look for an analytical solution. You would rather do experiments. So basically the advantage of CFD is that we can in industry scale, if we take whatever the problems or whatever the processes that are taking place at a very large scale, it is not feasible to do experiments for those cases. Like if we do experiments, there will be situations where we need to do scale up of those. It is not practically feasible. So in those cases, we move on to get CFD. It would be comparatively better to solve those system and get appropriate solutions. And also like analytical solution is not always feasible when we are dealing with large number of partial differential equations where it is not practically feasible to go into the solution process. So basically CFD is used in those cases where we use CFD to get the solution by appropriate things, procedures. So in those cases CFD would, we assume that CFD would give a reasonably correct solution. Similarly, in this case, it is given you wish to improve the performance of an exchanger by designing a better intake manifold because the cold airflow is not uniformly distributed. When such large heat exchangers are considered, we cannot practically do experiments and find out design how much airflow is needed. So in those cases, we go for a CFD by assuming that CFD would give reasonably correct answers, and that would be the true in most cases. So the answer for this question is option 1. Next question, it is question number 6. Here it is given that a client has produced a new catalyst that would improve the rate of a catalytic chemical reaction and wants you to check it out using CFD simulations. For this problems, which of the following statement is true? So it is given that we are dealing with a client who has produced a new catalyst and they want to improve the catalytic reaction by using the new catalyst. So they want to check it out using CFD simulations. So for this problem, which of the following statement is true? You expect CFD to give you reasonably correct solution. You expect CFD would not be of much use because you think reaction rate should be specified. And option 3 it is you expect CFD would not be of much use because you think flows with chemical reaction cannot be handled through CFD. You expect CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. So we'll go we'll go through the options one by one and see which of this is correct. You expect CFD to give you a reasonably correct solution is the option 1. In most cases, we expect CFD to give the correct solutions, but we also require certain things to be used in the problems. So this one is, since it is dealing with chemical reaction, we would be requiring some other terms also. So the next option is you expect CFD would not be of much use because you think reaction rate should be specified. When we are dealing with the chemical reactions, we do the problems in such a way that we consider the change in the concentration of a few chemical species to account for the mass conservation equations. So in those situations, we do species balance, and in that case we require this reaction rate. So we obviously think reaction rate should be specified. So this is option 2 is correct, and in option 3 it is given you expect CFD would not be of much use because you think flows with chemical reaction cannot be handled through CFD. This statement is not true because if we have or if we made chemical reaction like balance for species in the chemical reaction, we can proceed with CFD and it would not be a problem when reactions are considered. You expect CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. This is also not true because we can use a CFD when we are dealing with chemical reactions or catalytic chemical reactions, but we require certain things to be input into the system like reaction rate given here. So the answer to this question is option 2. You expect CFD would not be of much use because you think reaction rate should be specified. So answer is option 2. So it is given that which of the following statements is true about the use of finite difference approximations for solving CFD problems. So basically in this it is given finite difference approximations. We use finite difference approximation to discretize the given domain and basically solve get algebraic form of the equations, which can be solved to give the solution to this specific problem. So we'll see which of the following three statements is true about the use of finite difference approximation. So FD approximation can be applied to problems described in cylindrical coordinate system. This is for option 1, and it is on option 2. It is given for a given partial differential equation there is only one correct FD approximation, and in option 3 it is given FD approximation converts a partial differential equation into a linear algebraic equation. So when we are dealing with these equations, it is given that first one is FD approximations can be applied to problems described in cylindrical coordinate system. So obviously this is true. When we are dealing with cylindrical coordinate system or rectangular coordinate system, we can apply FD approximation to convert those equations into an algebraic equation. And in option 2 it is given for a given partial differential equation there is only one correct FD approximation. This statement is false because when we are converting a partial differential equation into algebraic form by using finite difference approximation, we can use various methods like central difference scheme, forward difference scheme, or backward difference scheme. So depending on the discretization scheme, there will be different methods. So it is not that there is only one correct FD approximation. There can be more than one. And FD approximation converts a partial differential equation into a linear algebraic form. It need not always be linear. It depends on the original domain. Based on the original system of equations or the differential equations, the partial differential equation will be converted into algebraic equations. So the answer to the question is option 1. So it is answer is option 1. So we'll see question 8. Consider the Laplace equation in a two-dimensional rectangular domain with Dirichlet boundary conditions. The equation is discretized at all interior grid points using second-order accurate finite difference approximation with uniform grid spacing in both directions. Which of the following statement is true about the resulting set of algebraic equations? It is given that we have a Laplace equation in two-dimensional rectangular domain. Dirichlet boundary conditions is used over here, and equation is discretized at all interior grid points using second order accurate finite difference approximation with uniform grid spacing in both directions. So which of the following statement is true about the resulting set of algebraic equations? So it is given that each algebraic equation will have exactly 5 non-zero coefficients. Each algebraic equations will have at most 5 non-zero coefficients, and it is given there will be at least one equations with only one non-zero coefficient. So we'll see how to proceed for this. For question 8, it is given that Laplace equation in two-dimensional rectangular domain and it is given that they have used Dirichlet boundary condition. So Dirichlet boundary condition is that where we specify the values at the boundaries. If we specify the values at the boundaries, that is known as Dirichlet boundary condition, and the other one is Newman boundary condition, where we specify the value of the derivatives at the boundaries. If we specify values, it is known as Dirichlet boundary condition, and if we specify the derivatives value at the boundaries, it is known as Newman boundary condition. Here in problem 8, it is given Dirichlet boundary condition, and and they've asked how the nature of the algebraic equations will be. So we'll see that. So we'll consider this equation. And let it be a function of some x and y in general, or if it is steady state, it would become 0. So here we need to discretize this equation. So there will be like we'll. So if this is the point I comma j, I comma j will be the center. So basically this will be j minus 1. I mean this whole region will be j minus 1. And similarly this will be j plus 1 if we consider in the y, this to be y domain. And for this will be I plus 1 and this will be I minus 1. So if we are to discretize this equation, we like in general we can put it like u I plus 1 comma j minus 2 u I comma j plus u I plus 1 comma j. If we are moving in the x direction, whole thing divided by delta x square will keep. And similar way for discretizing it in the y, for dou square u by dou y square, we'll get things like u. Here j will change rather than I. So it is u I j plus 1 minus 2 u I j plus u I j minus 1. So sorry, it is I minus 1. So whole thing would be divided by dy square. So from this we can see that we have like ui plus 1 comma j one factor, and here both of these factors are the same, ui comma j, and so it is 2, and ui minus 1 j, for that we have 3, ui j plus 1, and here you have ui j minus 1. So if we consider, there can be maximum of 5 coefficients that can be non-zero in this problem. So it is given that each algebraic will, it is not exactly 5 non-zero coefficients all the time. It will be at most 5 non-zero coefficients. So basically this equations is, from this we can see that there can be at most 5 non-zero coefficients, and there will be at least one equations with only one non-zero coefficient. This also need not be true to solve this problem. So the answer to this question is option 2. That is second option is the answer. And in question 9, it is given that you wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using Gauss-Seidel method. This method will converge if which of the following condition is satisfied. So the first option is matrix A is non-singular, and matrix, the spectral radius of A must be less than 1, and matrix A is irreducible and diagonally dominant. So when does Gauss-Seidel come into picture in CFD? It is that we have a domain for which we have partial differential equations. So similar to this, we need to get the solutions at each individual points in the system. So in order to get that, we convert the partial differential equations into algebraic equations by using by discretizing those equations. So we have that many equations. So in order to solve those equations, we should be having some iterative techniques. So Gauss-Seidel, we use it over there. In that place, we use Gauss-Seidel methods. So the first option is matrix A is non-singular. It is asked that when will Gauss-Seidel converge in this convergence criteria for Gauss-Seidel. So matrix A is non-singular. Non-singular matrix is that square matrix whose determinant should be a non-zero value. And in option 2, it is given that spectral radius of A must be less than 1. So spectral radius is for matrix A is that it is the maximum of the absolute value of the eigenvalues of the matrix A. And in but so we know that for solving Gauss-Seidel technique, we need the matrix to be non-reducible and it should be diagonally dominant. So option 3 is the must to solve the Gauss-Seidel methods. Otherwise, this will not give convergence. So answer is option 3. So in question 10, it is asked that which of the following statements is true about Gauss-Seidel iterative method for the solution of linear algebraic equations resulting from the discretization of the Laplace equation. So here also we have given 3 options and we should choose which is true about the Gauss-Seidel technique. So in option 1, it is mentioned that the method will always converge, and it is in option 2, it is given that initial guess at one grid point is sufficient for the method to get started, and in option 3, it is mentioned that the method will approach the exact solution asymptotically. So we'll go through the options one by one. So Gauss-Seidel iterative method for the given Laplace equations will always converge. So this will, if we discretize it and go through the problems in a step-by-step procedure, the method will, the equations will converge, and it is given that initial guess at one grid point is sufficient for the method to get started. This is not true because we need the values. If we are discretizing a rectangular domain, we need the values at all the boundary conditions. So initial guess at one grid point is not sufficient, and method will approach the exact solution asymptotically. So here it is mentioned that we'll get the solution asymptotically. It is nothing but we will consider the Laplace equation as let's consider this equation in rectangular domain. So let this be the Laplace equation, and so let it be like it will be dou square so for Laplace equations we'll put it as 0. So here we know that it will be a function of, for this equation it will be a function of x comma y. So basically we'll substitute this in this instead of w we'll put it as function of x and y. So we'll get that and on rearranging this we will be getting as 1 by a so basically d square f by dx square will be equal to minus c minus c into f, or this will be equal to g into c. So basically this will approach the solution asymptotically. That's what here it is mentioned. So option 1 and 3 would be right, whereas option 2 is not sufficient condition to get the convergence criteria. And here we'll see the next case and we'll solve the equations. So it is mentioned that the following notation is to be used wherever applicable. U is the velocity vector, U, V, W or velocity components in X, Y and Z. X1 Z and P is the pressure, mu is the viscosity, Nx and Ny are the direction cosines. So it is the flow through a triangular duct. We'll see a few questions for this. So it is given that you wish to compute the steady laminar fully developed flow field through a triangular duct as shown in figure 1. This is figure 1. For this case, the governing equation is given by, it is asked which is the governing equation. So we will see that in general, it is del dot u is equal to, we'll put like, basically the conservation equation, we'll write it like this. So if it is where it will be mentioned like dou u by dou x plus dou v by dou y plus dou w by dou z would be equal to 0. So basically, if we expand, if we consider fluid density, this will come like dou rho by dou t would come in addition, plus all these terms with a rho term will be coming over here. So basically this would be del dot rho u will be 0 for when we are considering flow. If when it is steady flow, this term would become 0, and basically the other terms that are remaining for a laminar fully developed flow would be del dot u is equal to 0 or del dot rho u is equal to 0. Those would remain from the conservative equation, if we cancel all other terms. And if we include the pressure terms, it would be like, uh, it would come like del dot del p. It would be like, we all know like in Navier-Stokes equation, dou p by dou x would come, that would be constant. So if we are taking derivative for this constant term, that would become 0. So del dot del p would be 0 and del dot u or del dot u would be 0. Del dot del p would be 0. Those would be the equations given over, would be true when we are computing the flow through this triangular duct. So not this, not this, and also not this. So none of the above is the answer. And it is given that you wish to compute the steady laminar fully developed flow through a triangular duct. For this case, which of the following is the admissible governing equations? So it is given that for the steady laminar fully developed flow through a triangular duct, which of the following equations would be considered? So it is given that dou square w by dou x square plus dou square w by dou y square is equal to 10, and dou square u by dou x square plus dou square u by dou y square is equal to 10, and dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p by dou x. So when we are uh, using this equation, we know that uh, when we are writing flow, Navier-Stokes equations and cancelling all the other terms, we'll be getting like dou square w by dou x square. This is Laplace equation with 10 right hand side constant. This would be true. Here it is given that u does not vary with x. So this equation is not true, and on the right hand side this should be a constant, so it would not be true. So option 1 is the correct answer. 1 is the only answer that is correct over this equation. So in question 13, it is given that for a steady laminar fully developed flow field through the triangular duct shown in figure 1, which of the following equations are applicable? So this question is an extension to the previous one, where we saw that del dot u would be 0 from the Navier-Stokes equation. If we cancel all other terms for considering the steady laminar and fully developed flow field, we get del dot u is equal to 0 and del p will be getting constant. And del dot del p, when we are taking one more derivative for del p, that would become 0. It would not be constant. So the answer to this question would be 1 would be correct and 2 would be correct, and this would not be this would be false. So 1 and 2, its answer is option 2. So question 4, it is given that if the order of a discretized equation is k, what does it mean? So in general, when we are discretizing any governing equations, it would be mentioned that it is of order k, or second order discretized equation. So what does it in general mean is that last term of the equation is of k plus 1th power, and last term of the equation is of kth power. Truncation error is proportional to kth power. Truncation error is proportional to k minus 1th power. So in general, what we denote when we are discretizing any equation is that we discretize the equation, and when the truncation error would be denoted by the kth power. So option 3 is the right answer. For example,
Ma'am, can you explain more about this? Why
one
this
second.
can be true?
Yeah, I'll just put that. Just a minute. I'll just So for example, we'll consider dou u by dou x. So basically, when we are using finite difference approximation and discretizing it, we'll expand this. We'll be using u I plus 1 comma j minus u I comma j by delta x, that is it would be dx. So this would be the thing that we would be writing, and we would mention it like this is of order 1. uh, what this denote is that this is of order. So when we are expanding this with respect to or okay, we'll go through in the reverse way. uh, for f of we'll consider f of x plus delta x. We'll be using it as f of x. When we are expanding this, we'll be using f of x uh, dou f by dou sorry dou f by dou x into delta x plus and so on. In a similar manner, if we are using this to expand this, like you in a similar manner, if we are using a equation u for getting u I plus 1 j, we would be using it as u I comma j plus dou u by dou x I comma j into del x plus dou square u by dou x square plus dou square u by dou x square into I mean at I comma j into del x square by 2 and so on. So when we are getting dou u by dou x at I comma j from this equation, we will be using it as these two. This will be there plus minus this, and minus of all other terms will be there. Sorry, this will be minus. So when we need only this, we will be using this will be there at I comma dou u by dou x at I comma j, and it would be equal to u I, this term will be there, and this delta x from the other side will come down, minus of this term will be there, and it would not be square. So basically what we do is we give only this value for dou u by dou x, and other rest other things we give it as approximation or truncation error. So this is known as truncation error. I mean is equal to, if we put it as this would be the finite difference approximation. For this would be this one, and my plus we call all other things as truncation error. So since we are using only this value, the rest other goes as truncation error, and we denote it as order of delta x. So basically all these terms we denote it over there. The truncation error is proportional to kth power. That is what we mean by order of the equation. That is, order of the discretized equation is k. It means that the truncation error is proportional to kth power. Since it is the truncation error here, it is, I mean delta x, it is order is proportional to delta x. Is that fine?
Uh, I understood some of it, but
Okay.
not all of it. Can you repeat the last two sentences that you just said?
Okay, what I mean is, like, when we are using finite difference approximation to get this algebraic equation for the partial differential terms, we
Mm-hmm.
ignore some terms from the, like, we generally use only this term, right? We do not
Right,
use all these terms, so
right.
we ignore it as truncation error. So
Mhm.
the order of the discretized form, that is for dou u by dou x at I comma j, this is the equation that we use. The order of this discretized equation is given by what are all the terms that we have ignored it as truncation error. Since from delta x we have ignored all the terms in this equation, the order here is delta x. If we have ignored it as delta x square, it would be second order. That is what
Yes,
we mean
the
by.
order of the partial differential is k, but the truncation error, the part which we have ignored, it starts from k square, right? Oh, sorry,
No,
k
no,
plus
no.
one, right?
Sorry.
I'm saying
I'm
that
I'm
uh,
talking about delta x, that term, not dou square.
yeah, exactly. I'm
Hmm.
also talking about that only. I'm
Hmm.
saying that the order of the daba u by daba x term, that is k, right? But the truncation error part which we are deleting, that is starting from k plus 1, right? So the truncation error, if that is considered as just the part which we are deleting or ignoring, so then that actually should start with k plus 1 na, then.
No, it is starting with k, right? Delta x power k. Like,
delta x squared, right? In the
No,
above,
it is in
in
this
the
term.
above here.
Yeah, in the above term it is delta x square, but in the final equation it is delta x, right? Like because of this delta x, we have cancelled one power
Okay,
in
okay.
whole, right?
Oh, yes. Okay, okay, got it.
I think because of writing it is not clear. So like since one delta x went off, it is delta x. That's what I meant. Fine.
Yes.
I mean, if you go with higher orders, it would be more clear. Like for dou square u by dou x square. If we put more equations and try solving it, it would be, for example, this is given like we are doing with forward condition. If we are basically going with 2 points like a central difference scheme like I plus 1 and I minus 1, that order would be different. It would not be the same always.
Hmm.
So, okay, we'll go to question 15. Which of these best define the Dirichlet boundary condition for the property phi at a point B in the boundary? So, it is asked that uh, for Dirichlet boundary condition, we know that the uh, value for the parameter will be given in Dirichlet boundary condition. In Newman boundary condition, we will give the derivative value of the derivative. So, which of these best define the Dirichlet boundary condition for the property phi at a point B in a boundary? So, the answer to this question would be, since all other questions we have given boundaries, sorry, we have given derivative. For question 4, it is question 15, the answer is option 4. Phi B, phi value at the point B is given. So, when we are dealing with Dirichlet boundary condition, the answer to this question is option 4. Over 50% of time spent in industry on a CFD project is devoted to definition of a domain geometry and grid generation. Which one will be the reason for this? More grids will give better results. Calculation time is directly proportional to number of cells. To generate non-uniform grids, to generate an optimal grid with a compromise between desired accuracy and solution cost. It is, for example, in when we are doing CFD simulations for large scale setup or large scale simulations, more than 50% of time would be in setting up the geometry and grid generation. The reason for this is we need a proper grid size, where we from which we will get the desired accuracy for the problems. At the same time, when the grid sizes are very low, it would give proper solution, but most of the time it would be a very the simulation time would be very large. So we do not want that large systems, and also in many cases the solution accuracy depends on exact or depends on the mesh size. Not, it is not always that a finer mesh gives better accuracy. It is not true. Depending on the system of we are solving, the mesh size should be proper. So more grids will give better results. It is like not always many more number of grids will give better results. It depends on the system that we are solving, and calculation time is directly proportional to number of cells. And to calculation time will obviously be more, but it finally what happens is that even though at some for few problems we put very finer mesh, it would not give solutions or it would not give proper solutions. It would go in a never ending loop sometimes. So, and to generate non-uniform grids, this is also not always required. But what is required is to generate an optimal grid that should be a proper compromise between accuracy and solution cost. We should see what we require in certain problems. So based on that, we design proper grid size. That is, in discretization scheme, we go for delta x, right? That is the grid size. If the, for example, Here we have given delta x, and consider this as a one small problem. Here we have divided it into four equal cells. In some problems we can divide it put one more grid over here, and we can put uh, 3 or 3 into 2 6, or we can divide it 4 into 2 or 4 cross 3, anything like that we want. Here the calculation will be somewhat simpler, like we know the values at this boundary, we know the values at this boundary, so based on that we can get the values in the center. But if it is one more if it is like divided into one more division is there, we would be calculating the value, we would be knowing this, from this we would be calculating this, from that we would be calculating. Here if consider the solution is somewhat like this. So if it is a better, if more number of points are there, the accuracy would be more than like 2 points are given, we would be getting only this. If 3 points are given, sometimes you would get better accuracy in terms of that. But the number of calculations or the number of equations that we are solving when grids are reduced to final size, that would be more. So we should find an compromise between the number of grid size, the number of grids that should be used in the simulation. And also that we should not compromise more by taking a larger grids. So the answer to the question would be to generate an optimal grid which is a compromise between desired accuracy and the solution cost. So answer is option 4. So these are the questions for today. If any of you have any doubts, we can discuss that now. Or we'll go through the questions, all the questions one more time. We'll wait for 2-3 minutes. If no one has questions, we'll go through the questions, all the questions one more time, quickly. Okay, we'll quickly go through the questions once again. So this is problem 1. Here we are solving a Here we are solving case 1. In this case, it is given that you wish to solve a problem involving steady heat conduction with source term. In case of one-dimensional flow, this takes the form Q is equal to K d square T by dx square, where K is the thermal conductivity of the material, T is the temperature, and Q is the volumetric heat generation rate. For this case, we should answer the following questions. For equation 1 to be dimensionally consistent, what should be the units of Q? Here it is uh, Q should be Q is equal to K d square T by dx square. We know the unit of K to be Q is equal to K d square T dx square. So they have asked unit of Q. So it is K is watt per meter Kelvin into Kelvin for T by meter square for dx square, and putting together all this we'll get watt per meter cube. Since we K and K would get cancelled, and this would be nothing but joules per second meter cube. So this is question answer to question 1, and in question 2 it is asked that we wish to solve a for heat steady state heat temperature distribution in a rod of length L and the variation is only axial. Which of the following boundary condition is admissible? It is given that temperature at both the ends is given, temperature heat flux at both ends is given, heat flux and temperature at one end, and heat flux and temperature at other end. So basically to solve the equations we need boundary conditions, that is yeah, yeah. Sorry, I could not hear you. Can you please repeat it? Hello? Hello? I did not understand. Can you please repeat it? Okay, fine. We wish to solve for steady state temperature distribution in a rod of length L and the variation is only axial. Which of the following boundary condition is true? So as we know that we need values at both the boundaries. So it can be temperature at both the ends or temperature at one end and a derivative at the other end. So heat flux at the other end. So both of this is possible, but heat flux at both the ends or heat flux and temperature at same end is not feasible. So answer to this question is option 3, which is option 1, and option 4 is correct. So in question 3 it is given that for equation 1 to be one dimensional, which of the following can be true? So since it is given that it is one dimensional and steady state, it is q is equal to constant is possible, q is a function of x is possible, q function of t time it is not possible, and q function of both time and t is not possible, because it is clearly mentioned that it is a steady state problem. So option 1 and option 2 are only correct. So it is answer to this question is number 1. So which of the following is an admissible extension of equation 1 to steady heat conduction in 2 dimensions? So we know that the equation is q is equal to k d square t by dx square. So which can be extended to 2 dimensions. So dou square t by dou x square plus dou square t by dou y square is equal to q. That is q is constant over here. Here the option 1 is not feasible because it is becomes non-linear with respect to x only. This is not a direct extension of equation 1. In same way, here it is given an unsteady state problem, which is also not true. So option 2 is only the correct answer. And in question 5, we have seen that you wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold. Because the cold airflow is not uniformly distributed across the heat exchanger, you wish to study this using CFD and arrive at a better design. For this problem, which of the following is true? So it is asked that which is true. You expect CFD to give a reasonably correct solution. You expect CFD would not be of much use. You would look for an analytical solution. You would rather do experiments. CFD is mainly useful in cases where analytical solution is not practically feasible or we could not do experiments at such large scales. In both of these circumstances, we go for the CFD. So since this is one such area where air-to-air heat exchanger, we need a design improvement which cannot be possibly done with other tools. So we expect CFD to give us a reasonably correct solution. So in question 6 is similar to question 5. Here it is given that a client has produced a new catalyst that would improve the rate of a chemical reaction and wants you to check it out using CFD simulations. For this problem, which of the following statement is true? The first, it is given CFD would give correct solution. And second, it is given you expect CFD would not be of much use because you think reaction rate should be specified. And we expect CFD would not be of much use because we think flow with chemical reaction cannot be handled through CFD. CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. So since it is a chemical reaction, CFD can be used to solve for specific chemical reaction. But the thing is, we go for concentration balance or mass balance, where concentration of different species comes into play. In such cases, we need to know the reaction rate to correctly solve the problem. So, for this question, the answer is option 2. We expect CFD would not be of much use because we think reaction rate should be specified. And in question 7, it is given that which of the following statements is true about the use of finite difference approximation for solving CFD problems. It is given that FD approximation can be applied to problems described in cylindrical coordinate system. For a given partial differential equation, there is only one correct FD. For a FD converts a PDE into linear algebraic equations. Of all these things, the answer to this is FD approximation can be used to do cylindrical coordinate systems, but it is not true that it is only one FD approximation because there are various techniques like forward difference technique, backward difference technique, and central difference scheme to discretize the given partial differential equation. So considering all those things, it is not always true that FD is only gives one correct answer. And also FD approximation converts the PDE into linear algebraic equation. It need not be true. It can be, or in some cases it cannot. It can be false. So option 1 is the correct answer. Consider the Laplace equation in a two-dimensional rectangular domain with Dirichlet boundary condition. The equation is discretized at all interior grid points using second-order accurate finite difference approximation with uniform grid spacing in both directions. Which of the following statements is true about the resulting set of algebraic equations? Each algebraic equation will have exactly 5 non-zero coefficients. Each algebraic equation will have at most 5 non-zero coefficients. So, based on this equation, when we discretize partial differential equation, when we discretize the Laplace equation with Dirichlet boundary condition, we discretize it as for 3 different points using the central difference scheme. Considering this, here we have 5 unknowns, 5 coefficients which should be solved. So the maximum number of unknowns that can be in the equation is 5. It will not be exactly 5 because when solving for the boundaries, we know the values, so it would be less when we are substituting the cases for the boundaries. And also there will be at least one equation with only one non-zero coefficient. This also need not be true. There will be more than one. Maximum there will be one or two coefficients that would be going because of boundary conditions. Other than that, all the points would be getting in the form of discretized equation. So in question 9, it is given that you wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using Gauss-Seidel method. This method will converge if which of the following condition is satisfied. Matrix A is non-singular. Matrix A is irreducible. Spectral radius of A must be less than 1. And in option 3, it is given that matrix A is irreducible and diagonally dominant. To solve Gauss-Seidel equations, it is required that matrix A is not required for A to be non-singular for getting the convergence, and spectral radius of A it need not be less than 1. But the main criteria to get solutions from Gauss-Seidel technique is the matrix A, that is the Ax is equal to B, that matrix A should be irreducible and it should be diagonally dominant. So option 3 is the correct answer. For question 10, moving on to question 10, we have that which of the following statement is true regarding Gauss-Seidel iterative method for the solution of linear algebraic equations resulting from the discretization of Laplace equation. So when we discretize the Laplace equation and get Gauss-Seidel method, for the iteration to converge, what is the criteria? The method will always converge. Initial guess at one grid point is sufficient for the method to get started. Method will approach the exact solution asymptotically. So in this system, it is that method will always converge and the solution will approach the solution asymptotically. But initial guess at one grid point is not sufficient to get started. We need all the boundary condition values to get the system to solve the set of equations in the system. This is the method of how we are getting asymptotical solution, of how we are saying we are getting asymptotical solution when we are solving Gauss-Seidel method. So this is case 2 where it is given that the following notation is to be used wherever applicable. U is the velocity vector, U, V, W are the velocity components in x, y, z coordinates, P is the pressure and mu is the viscosity, and Nx and Ny are the direction cosines. So it is the problem where we are considering flow through a triangular duct. In question 11, it is mentioned that you wish to compute the steady laminar fully developed flow field through the triangular duct. For this case, the governing equation is given by which of the following it is given. When we are solving flow through a fully developed flow through a rectangular duct, the criteria is that del dot u is 0. So for question 11, the condition that would be mostly applicable would be del dot u would be 0 when we are considering the velocity vector, or del dot rho u would be 0. Rho u would be 0 when we are considering fluid compress. When we are considering incompressible fluids, and the other thing would be del dot P, that is pressure gradient. Delta P would be a constant, and del P would be 0. So these are the criteria that should be considered when considering flow through triangular duct. So since not any of this option is true, the answer to this is none of the above. And you wish to compute, in question 12 it is given that you wish to compute the steady laminar fully developed flow field through the triangular duct. For this case, which of the following is an admissible governing equation? So it is given that dou square w by dou x square plus dou square w by dou y square is equal to 10. It was for flow we give like dou square w by dou x square plus dou square w by dou y square is equal to 10, that is constant. This is feasible. Here it is given dou square u by dou x square plus dou square u by dou y square is equal to 10. U is not a function of x. U is only a function of y and z. So this term would become 0 if it is a k. So this is false. Dou square w plus dou x square plus dou square w by dou y square is equal to constant. Here also this term would be 0. So option 1, that is 1 only, is the correct answer. So moving on to question 3. For a steady laminar fully developed flow field through triangular duct shown in figure 1, which of the following equations are applicable? So it is given that we saw in previous question itself that these are the criteria that should be checked when we are solving the problem in flow field. When we are putting this, considering this criteria over here, del dot u is equal to 0. So option 2 is correct. Delta P is equal to constant. Option 1 is also correct. And delta P is equal to 0. When first criteria itself is true, the other things should be it should be 0, not constant. So it is option that is third one is false. So 1 and 2 are only right. So option 2 is the correct answer. In question 4, it is given that which of the order of a discretized equation is k. What does it mean? Last term of the equation is k plus 1th power. Last term of the equation is kth power. Truncation error is proportional to kth power. Truncation error is proportional to k minus 1th power. So which of the following is correct? So it is generally truncation error is proportional to kth power. So we will see how it is given. This is for question 14. Consider this dou u by dou x at I comma j. We generally use this form of expression ui plus 1 comma j or minus ui minus 1 comma j by delta x. How does this term come is that, for example, consider the Taylor series for fx plus delta x. We give it as f of x plus dou f by dou x into delta x plus dou square f by dou x square into delta x square by plus 2, plus there will be many other terms. In a similar fashion, if we write for ui plus 1 comma j, we get ui comma j plus dou u by dou x at I comma j into delta x plus dou square u by dou x square into I comma j plus delta x square by 2 and so on. If we keep only this term and take all other terms to the right hand side, we get this form for this equation ui plus 1 comma j minus ui comma j by minus this terms will be remaining. So if we take the delta x also to this side, we get bottom delta x and delta x by 2. So we generally denote this term as delta x, that is for first order finite difference approximation. We denote this term using finite difference approximation, and so this would be finite difference approximation, and all the other term we would be denoting as truncation error. So here it is basically seen that truncation error term is delta x. So the order of this is first order, that is delta x. Kth power, that is first power, that is first power. So for example, if we expand this using central difference scheme than the first order scheme, it is I plus 1 comma j minus I minus 1 j by 2 delta x, and all other remaining terms will be there. So basically what would happen is that this is the power of delta x square. So here it is second order. So central difference scheme is second order. Central difference scheme, and it is first forward difference scheme. Which of these best define the Dirichlet boundary condition for the property phi at a point B in an inner boundary? So this is given by this equations 4. Phi B is the Dirichlet boundary condition for the property phi at point B. Dirichlet boundary condition, we give the values than giving the derivative value. So the boundary condition is phi B. Like if phi value is given at the point B, it is known as Dirichlet boundary condition. If dou phi by dou x is given at point B, this is known as Newman boundary condition. So in question 16, it is given that over 50% of the time spent in industry on a CFD project is devoted to the definition of the domain geometry and grid generation. Which one will be reason for this? More grids will give better results. Calculation time is directly proportional to the number of cells. And to generate non-uniform grids, to generate an optimal grid, which is a compromise between desired accuracy and solution cost. When we are dealing with CFD, the main thing to be considered is grid generation. Grid generation is nothing but here we are discretizing the domains. These domains are known as grids. Like this is here. If we consider the smaller domain, we have 1, 2, 3, 4 cells in this. So we are discretizing it by giving values I comma j, I plus 1, and this is j plus 1, this is j minus 1. So basically this would help us in making the partial differential equation into the algebraic terms. So on using this, we have that thing, right? Um, the major thing to be considered in solving any CFD problem is optimal grid generation. If the grid sizes are very much finer, it is not guaranteeing that the solution would be so much accurate. In some cases, the grid solution should be such that we should uh, do proper meshing. So based on the problem specification, and also like if it is too much finer, the computational cost will be very much increased. So there should be always an optimum compromise between desired accuracy and also the solution cost. We should not always go for finer meshes because we can't do large computations, and similar way larger grid size would give faster computing, but the results would not be accurate enough to solve in large scales. So the answer to this question is to generate an optimum grid, which is a compromise between desired accuracy and the solution cost. So these are all the problems for this session. So the first 10 questions were from assignment 1, and remaining questions are randomly taken. So that's it for today, and thank you very much for attending this session. If anyone has any doubts, you can please ask. one last time we'll go through the problems. So the first question was this one-dimensional problem, q is equal to kd square t by dx square. So based on this problem, we found out the units for q by using dimensionally consistent approach, and based on this we also found out what are the boundary conditions that should be used to get the values. So things to be remembered here is that we need values at the both the ends, or value at one end and the flex at the other end. In question 3, based on this, we can see that Q is a one-dimensional problem and steady-state problem. So it is a function of position, or it would be constant. And in question 4, it is given that q is equal to k d square t by dx square. Here q can be constant, and also k is not it is not dependent on x. So the option 1 is wrong, and also it is not a steady state problem. It is not an unsteady state problem. So option 3 is also wrong. And in question 5, it is given that which of the following, how would we select CFD? In question 5 and 6, both the problems are same. The first one is a heat exchanger problem. Therefore, we give a better design by considering CFD would give better solution for us. Whereas in question 6, it is a chemical reaction problem. Basically in this problem it is given that we need to know the concentration or rate, reaction rate, to get the problem to be given solution through CFD. And in question 7, it is about finite difference equation. In finite difference equation, it can be applied to cylindrical coordinates also, but it is not true that there is only one partial solution for the partial differential approximation. Also, it is not always converting PDEs into linear algebraic equation. Laplace equation is given, and boundary condition, Dirichlet boundary condition is given. So it is given on discretizing it, we observe that there are maximum 5 different non-zero coefficients, and from this it is true that when Dirichlet boundary conditions are given, the number will be reduced. So it is maximum 5 and minimum it can be anything. Also, when solving Gauss-Seidel approximation, the solution will converge when the matrix is reducible and is diagonally dominant. And similarly, Gauss-Seidel gives a convergent solution when we are solving it for Laplace equation, and it will give the exact solution asymptotically to this is a triangular duct flow problem. So based on this, we need to solve these equations. So in the first thing, it is given that the thing to be noted here is that when solving for triangular duct or flow through any problem, for a steady laminar incompressible flow or any flow, the first one is for incompressible flow. Del dot u is equal to 0. When it is compressible, del dot rho u is equal to 0. And for the pressure gradient term, it is delta P is equal to constant. Del dot delta P would be 0 in such cases. And extension to the one-dimensional equation in two-dimensional form would be dou square W by dou square X square plus dou square W by dou Y square is equal to 10. That is constant. U is not a function. U is a function of Y and Z only, not X. And also here it is constant. So option 1 is the correct answer. So based on the criteria, we can observe that delta P is equal to constant and delta U is equal to constant for the same flow, steady laminar fluid flow through a triangular duct. So this is given by this equation, and it is observed that option 1 and 2 are right. Option 3 is not, it's constant, it is 0. So answer is option 2. And if the order of a discretized equation is q, what does it mean? It means that the truncation power is proportional to kth power. This we saw by discretizing a single term and observing how the truncation error forms the risk for the finite differential approximation. And digital boundary condition, I know that it is the value at the boundary. So if the property P pi is given at boundary point B, this is known as Dirichlet boundary condition. If the flux of that point is given, that is Newman boundary condition. And the last session is 450% of time spent in industry on a CFD project is devoted to definition of domain geometry and grid generation. So the reason will be to generate an optimal grid, which is a compromise between desired accuracy and the solution cost. All other things are also true, but that is not the reason why we are devoting that much time. It is because we need an optimal grid with a proper solution and accurate solution, that with uh, time, with like solution time that is feasible for us. Computational efficiency must be there. If solution time is very large, it is not always practically feasible to run many simulations. So the answer is option 4, to generate an optimal grid with the compromise between desired accuracy and solution. So thank you. That's all for today. Thank you so much for listening to this session. Thank you. Thank you. So we'll close the session now.